In this video, we're going to take a look at tangent planes. So suppose we have a surface in three-dimensional space. Let's say our surface has the usual equation z equal f of x, y. So I've drawn the axes on here just really to emphasize that we are in three-dimensional space. And this is just a visual representation of what a surface might look like. So what we're interested in talking about is the tangent plane to our surface at a given point. So let's say you identify any point on this surface, maybe this one, and associated with that point, there will be a unique tangent plane. So let's draw a picture of what that tangent plane looks like. So let's say it's that plane right there. So roughly speaking, the tangent plane is the unique plane that contains your given point and does not intersect the surface at any nearby points. So the tangent plane essentially comes in, touches the surface just at that point, but it just touches the surface. So what we're working towards is finding the equation of the tangent plane to a surface at a certain point, and in order to do that, we need to know something about the normal vector to the tangent plane. So the fact is that a normal vector to the tangent plane is given by the following formula. So we're going to use little n to represent our normal vector, and the formula for that minus z sub x minus z sub y, 1. Okay, geometrically, what the normal vector represents, it's a vector that's perpendicular to our tangent plane, and that's really essential to finding the equation of that tangent plane. So let's see how to use this fact to solve a problem. So let's find the equation of the plane tangent to the surface, z equal 12 minus 4x squared minus 3y squared, at the point where x, y, z equals 1, 2, negative 4. Well, first thing we'll start with is just calculating this normal vector. So according to our fact, the normal vector is going to be minus z sub x minus z sub y, 1. So partial of z with respect to x is going to be minus 8x, but there's a sign change, so it becomes 8x. Partial of z with respect to y is going to be minus 6y. Change the sign on that to get 6y, and then comma 1. Okay, so now what we're going to do to get some specific numbers here for the normal vector, we're just going to sub in our coefficients, or our coordinates rather, for our point. So we're going to use x equal 1 and y equal 2. So that way, by subbing in, you're getting the specific normal vector for whatever point in space you're interested in. All right, so in general, I don't usually write that part down. So let's just sub in here for the specific coordinates. So 8, 12, 1 is the normal vector that we're going to be working with. Now you may remember from linear algebra, what the normal vector does is it gives you the coefficients for x, y, and z in the equation for your plane. So anytime you've got a normal vector to a plane, anywhere throughout linear algebra, the components of that normal vector are going to give you the coefficients of x, y, and z in your equation. So we can jump from this normal vector just immediately to 8x plus 12y plus z equals some unknown number. So I'm just going to write d here. And the way we're going to get our d value is now to sub in x, y, z equal 1, 2, negative 4. Okay, so let's sub in x, y, z equal 1, 2, negative 4. Incidentally, sometimes in this type of problem, they'll just give you an x and y coordinate as opposed to a z coordinate. If you just had x and y, you could figure out z just by plugging into the formula for your surface. So if you just knew that x was 1 and y was 2, you could figure out z equal negative 4. All right, so subbing in x, y, and z there, let's see what we get. 8 plus 24 minus 4 gives us our d value. So in other words, d is 28. And we can then take that, plug that back into the equation to get our final version of our tangent plane. So 8x plus 12y plus z equals 28. That is the unique tangent plane that comes in, just touches the surface at this point, 1, 2, -4. Okay, now a slicker way to do this kind of reasoning, if you're really up on your linear algebra, you might remember the normal form for a plane. So you could have actually written n dot x equals n dot p, just makes this whole process a little cleaner. N being your normal vector, so the 8, 12, 1, dotted with your vector of variables is equal to that same normal vector dotted with the vectorized version of the point that you're working with. So 1, 2, -4. And that way, by computing the dot products on both sides, you'd have 8x plus 12y plus z equals, and numerically still going to come out the same as before. So just a completely equivalent way of doing it. Just depends on whether you really like the normal form from linear algebra to do this slightly more cleanly. So that's an example of calculating the tangent plane to a surface at a given point. Thanks for watching.